Alright, section 6.4 actually brings us to what we call the fundamental theorem of calculus. So you can see how that might be a really important section to cover in calculus. The fundamental theorem of calculus. So we're going to take this idea of integration, we're going to add in one little extra step. And what we're going to do is we're going to take that integration symbol and we're going to put two values. We're going to put a number at the top and the bottom of that integration symbol. When you have a number at the top and the bottom, we call this the definite integral. So we have a function f, and it's defined on what we call the closed interval from a to b. This is the smaller of the two numbers, and this is the larger of the two numbers. Okay. So this is called the definite integral when you have a number at the top and the bottom. The previous sections that we've looked at have been dealing with the indefinite integral. So section 6.1 and section 6.2, we talked about finding the indefinite integral. Okay, in all of those, we did not have a number at the top or at the bottom. So here we're looking at the, I'm going to spell that. So here we're looking at the definite integral. So how do we use this definite integral? Well, the number a is called the lower limit of integration, and the number b is called the upper limit of integration. Okay. There is a geometric interpretation of what we're actually finding. When we evaluate or find the definite integral, we're actually finding the area between the curve of the function and the x-axis. So that is the area that we are actually finding. Okay, so here's actually what brings us to what we call the fundamental theorem of calculus. So the fundamental theorem of calculus says the first thing that you're going to do is you're going to find the antiderivative. And we've been doing this. We've been doing this in section 6.1 and 6.2, so that is nothing new. In part 2, actually says after you find the antiderivative, you are going to take the upper limit and you're going to plug the upper limit of integration into the antiderivative, and then you're going to subtract from that the lower limit put into our antiderivative. So we're going to find a number, and that number that we find in the end is going to represent the area between the curve and the x-axis. Alright, so we're going to kind of look at an example. We're going to look at a good visual of what we're actually trying to accomplish here. Alright, so this says we want to find the area of the region under the graph of the function f on the given interval. So here we're given the function f of x equals 4 minus 2x. Remember that f of x really represents the same thing as y. And I could rearrange the terms in whatever way I want. So this is really the same thing as y equals negative 2x plus 4. What does that sound a lot like? That sounds a lot like a line that has a slope of negative 2 and a y-intercept of 4. So before we do anything, let's just look at the graph of what we're talking about. So we're talking about a line that has a y-intercept of 4, and then a slope of negative 2. So I'm going to go down 2 to the right 1, down 2 to the right 1. So here's our curve. Alright, so there's our curve. What we're looking at is to find the area between the curve and the x-axis. Now we're not looking at the entire curve. This tells me to look between 0 and 2, and these are x values. Okay, and 0 would be called the lower limit of integration, and 2 would be called the upper limit of integration. That's the a and the b. So x equals 0 is right here, and x equals 2 is right here. So the area that we're actually going to end up finding is this area right here, between the curve and the x-axis, and in between x equals 0 and x equals 2, and it looks like a little triangle there. We're going to find the area of that. So here's what we're going to do. To find this area, we are going to integrate the given function 4 minus 2x. We're going to integrate that with respect to x. And our smaller number, the lower limit of integration will go at the bottom. And the larger number, the upper limit of integration will go at the top. So the first thing you want to do is we want to find what is the antiderivative. That's really easy to find, right? We've been doing that several times in the last two sections. We've done that several times. So 4. The first term is 4. So the antiderivative of that would be 4x. All right, remember if it's just a constant, we're just going to multiply by x. What about minus 2x? Well, the exponent on x is 1. All right. Let's just do this. We're going to add 1 to the power. We're going to divide by the new power. And then we're going to bring down that constant multiple. All right. So there's our antiderivative. Now, can we make it look simpler? Yeah, we can cancel out the 2's. And there we go. Step 2, all right, brings us to the fundamental theorem of calculus. And what does it say? It says once you find that antiderivative, which the definition calls this capital F of x as the antiderivative, once you find that antiderivative, what we're going to do is we are going to evaluate that. So we're going to plug in some values for x. And usually when you look in your book, you'll see a straight line, and then it'll put a 0 here and a 2 here. These are the limits of integration. We always put in the larger number first. So here's what I'm going to do. I'm going to take that entire function, take our entire antiderivative, and I'm going to replace x with 2. Right? Then we're going to subtract from that the lower limit of integration plugged into that antiderivative. Okay, what I like to do when I do this is I put little brackets. And then I write the entire function, the entire antiderivative, without the x's. I put parentheses, and then I put my larger number in first. And then notice that that is exactly the same thing that I have after the minus sign in the brackets here. I have minus, brackets, 4 times x minus 2 times x squared. So I'm going to replace, sorry, this 2 shouldn't be here. So you want to copy what you have here exactly, except for leave off the x values. So for this, what am I plugging in? Now I'm plugging in the lower limit of integration in place of x here. So we're plugging in zeros. All right, so we take my antiderivative, put it in the first bracket, minus, take that same antiderivative, put it in the second bracket. The first bracket, you put 2 in place of x. And in the second bracket, we put 0 in place of x. Okay, so this is using the fundamental theorem of calculus. We find the antiderivative, and now we're just going to plug some values in. Larger minus smaller. So what do we get? So I get 8 minus 4. And then here I get 0 minus 0. That's really nice. So I get 4 minus 0. And so my final answer turns out to be 4. Remember, this was supposed to be the area of this region between x equals 0 and x equals 2 and under the curve and between the x-axis. Let's recognize something. Does that 4 make sense? Let's go back to what we've known from geometry a long time ago. How do I find the area of a triangle? See if it goes back to what we know. The area of a triangle. The area of a triangle would be 1/2 the base times the height, right? So that'd be 1/2. What's the base? The base is 2 units long. So that's 2. What's the height of our triangle? The height of the triangle looks like it's 1, 2, 3, 4 units tall. 1/2 times 2 would be 1. 1 times 4, we end up with an area of 4. So the old way of finding the area of a triangle and the new way of finding the area of a triangle give us exactly the same answer. Now, why didn't we just use the area of a triangle? Well, we're trying to learn this new method here, right? So once we know the new method and we see that it coincides and actually does find what we want, now we can do more complicated things that we don't have formulas for. All right, so let's look at the next example. So the next example is really interesting because we have this curve. So this is not one of those nice, neat shapes. And I've already graphed it over here for you. we have this curve, and we want to find the area between the x-axis and the curve from -2. So I'm going to go ahead and just mark off x equals -2, which is right here. All right. All the way to x equals 6. So from here to here. Oops. Let's make that more straight. Okay. So remember what we're looking for. We're looking for the area between the curve and the x-axis. So I'm looking for this area here. And I'm actually going to find this area here and this area here. Okay, so between the curve and the x-axis, okay, and in between -2 and 6. Here's one little extra thing I'm going to throw at you. When we do the integration thinks about any areas above the x-axis as being positive areas. Okay. It thinks about anything below the x-axis, any of those areas below, as being negative areas. So before we start, do you think our answer would be positive or negative? Well, it looks like we have more area below the curve, below the x-axis rather. Looks like we have more area below the x-axis than we do above. So my guess would be that we would end up with a negative answer because we have more negative space than we do have positive space. Okay? But let's see what happens. How do I find the area? Well, to find the area, we want to integrate. And what I'm going to do here is I'm going to go ahead and just distribute to make the function look a little bit easier. X squared minus 5x. We're going to integrate that function with respect to x, and we're going to go from the smaller number, the lower limit of integration, to the upper limit of integration. All right. So this is going to give me the area that I want. Okay. So the first step is to find the antiderivative. Okay. So the antiderivative. Well, we have x squared. That's our first term. We're going to add 1 to the exponent and divide by the new exponent. So here we have -5, which is a constant, times x. All right, now our exponent is 1. So we're going to bring down the constant. We're going to raise the exponent. We're going to add 1 to that exponent and divide by the new exponent. All right. And the next thing we said was we want to evaluate this antiderivative from the upper and lower limits of integration. So we're going to use that fundamental theorem of calculus. So in order to do that, step 2 here continues. What we're going to do is I'm going to take the antiderivative and I'm going to copy it down exactly as I see it. And I'm going to put minus, and I'm going to do the same thing again. All right. Now we're putting in first, into the first brackets, we're putting in 6, the larger number of the upper limit of integration there, so the larger number of the two. And then we're putting in the smaller number into the parentheses second. So into that second bracket, we put the smaller number. So larger, smaller. And now we're going to simplify these fractions. So off the top of your head, you might not know what 6 cubed is, but you have a calculator. So that gives me 216 over 3 minus, so over here we have 6 squared, that's 36. 5 times 36, put that into your calculator, you should get 90. So I write 90 over 2. All right. Okay, now both of those might just simplify, so let's see if we can go a little bit further with the simplification there. So you put into your calculator 216 divided by 3, you get 72. So we actually get something nice. 72 minus 45. Okay, and then all of that turns out to give me negative 18. Okay, now we're going to subtract from that what comes out of our second bracket here. Okay, negative 2 cubed, you can throw that into your calculator, you get negative 8. So I get negative 8 over 3. Negative 2 squared is 4. 4 times 5, that's negative 20 over 2. What I would like to do is write that as negative 10, right? That will make things a little bit easier. So negative 8/3, negative 10, there we go. Let's distribute the negative before we start dealing with fractions. So that negative would distribute and change the sign. So that would be plus 8/3 and then plus 10. So we want to combine all of these numbers together now. So now we have negative 18 plus 8/3 plus 10. Let's combine all of those numbers together. Well, negative 18 and 10, that gives me something pretty easy. That gives me negative 8. But I do want to add 8/3 to that, which means I want to give a common denominator. So the common denominator, of course, would be 3. So that gives me negative 24 over 3 plus 8/3. So I get a final answer of negative 16 over 3. So this represents my area. Now we said we anticipated that we might get a negative value, and that's because these positive areas are smaller than this larger negative area. So it does make sense that we would end up with a negative value for the area between the curve and the x-axis. Alright, so our next example, we want to do the same thing. I want to find the area between the curve and the x-axis and between x equals 1 to x equals 2. So if I'm looking for the area, we want to integrate from 1 to 2, so from the smaller number to the larger number goes on top. We're going to integrate 1 over x with respect to x. So we said the first thing you want to do is find the antiderivative. Okay, well, what is the antiderivative of 1 over x? Pretty easy. We know that's ln of x. Alright, now we're going to evaluate that. Our second step is to evaluate that from the upper and between the upper and lower limits of integration. So we know we're going to write out our antiderivative twice. So ln of x minus ln of x. So I recommend setting this up first. Just do this every single time. Bracket minus bracket. So we're always subtracting. Write the antiderivative without x in the first bracket. Write exactly the same thing in the second bracket. Now what's going to go in place of x? In the first one, we put the larger number here, put the smaller number here. Alright, and now we are going to simplify. So this turns out to be ln of 2 minus the natural log of 1. Put that into your calculator, you get 0. Okay, so that's pretty easy. If you put ln of 2 into your calculator, you end up with 0.693. So 0.693 minus 0. I'm going to be clear about something. The exact answer would be ln of 2. Okay, this gives me an approximate value of 0.693. So either one, whatever WebAssign asks for, you can give them that. The exact answer would be ln of 2 minus 0, which is just ln of 2. The approximate value, if I put that into my calculator, I get 0.693. Okay, remember this represents the area between the curve that we were given for the function and the x-axis. If you want to, you could do this. You could also graph this in Desmos on your own. So you could graph that in Desmos and then look between 1 and 2, and you will see that the area would be approximately 0.693. So you can put that in Desmos, you can kind of get a good picture of what the area is that you actually found. Alright. Now, this example, the directions say to evaluate the definite integral. So on the exam, you're going to have two different types. You're going to have evaluate the definite integral and also the indefinite integral. Okay, what's the difference between the two? Remember, the definite integral comes with these numbers at the top and the bottom of the integration symbol. So we want to keep that in mind. Okay, what that means. That means that we're going to find the antiderivative first, and then we're going to use that fundamental theorem of calculus. We're going to plug those numbers into the antiderivative. All right, so we're going to find the antiderivative. So the first thing I'm going to do is I'm going to rewrite this as 3 times u to the 1/2 power du. And I'm going to go a little bit further with the rewriting. I'm going to bring that constant multiple outside of the integration symbol. I'm going to make this a little bit smaller there. Okay, so we want to find the antiderivative now of u to the 1/2 power. So we're going to add 1 to the exponent. So that gives me u to the 3/2 power. We're going to divide by the new exponent. We're going to bring down our constant multiple. And we're going to simplify this a little bit. So take the denominator, that fraction, let's multiply by the reciprocal of that. And we actually end up with 2 times u to the 3/2 power. Okay, remember we're going to evaluate this from 1 to 9, so the upper and lower limits of integration. Now, let me ask you this question. How come we haven't done the plus c? We found the antiderivative in the past, we've always done plus c. Let's explore that, okay? Let's talk about why we don't do plus c now, okay? Let's just say I put the plus c here. I want you to see what's going to happen every single time if you were to put the plus c, what's going to happen every single time, and that's going to explain why we don't do it anymore, okay? So when I evaluate this, so let's say that I come up here, and remember we're going to use the fundamental, let's just abbreviate this, fundamental theorem of calculus, okay? Remember what we're going to do is we're going to take the antiderivative that we just found, and we're going to put it into these brackets. So that's 2 times u to the 3/2 power plus c, 2 to the 3/2 power plus c. All right, what are we putting in the first one? We're putting in a 9. Remember we put in the larger number first, and then we put in the second number of 1. So the smaller number goes into the second bracket. Okay, so remember that when we evaluate something to the 3/2 power, that's the same thing as taking the square root and then cubing it. So let's take the square root of 9 and cube it. Remember, 9 to the 3/2 power is the same thing as the square root of 9 raised to the power of 3. So that's what we're going to be thinking about as we go through. Okay, so let's figure out what that is. Okay, square root of 9 is 3. 3 cubed turns out to be 27. So we end up with 54 plus c, and then we're going to subtract. This was really nice and easy. The square root of 1 is 1, and then 1 cubed is 1. So we end up with 2 plus c. Okay, so here's where we're going to talk about why we don't and why we haven't written the c. Every single time that I do that, what's going to happen? Well, I'm going to do 54 plus c, and then what's going to happen here is I'm going to distribute the negative into the second bracket. I get minus 2 minus c. Because we're always subtracting, what in the end would happen with the c's is that this c and this c would always end up canceling out. So we'd always end up with a positive c and a negative c. So we don't write the c's anymore. So we don't write the c when we are doing definite integrals, integration, let's say, because of the fundamental theorem of calculus. So this is why we don't do it, because the c's would always end up canceling out, so we'd always end up with just 54 minus 2, which gives us, of course, 52. So we'd always end up with just the numbers anyways. So that's why we don't write the c's. So if you're wondering, why haven't we written the c's? And that's because when we use the fundamental theorem of calculus, the c's always cancel out. So here we have plus c, here we'd always end up with minus c, so they'd always end up canceling out anyways. So we just skip writing them because we know the end result. All right, so the area that we found there, 52. Okay, here we're asked once again to evaluate the definite integral. How do we know it's a definite integral? Well, because we see the 0 and the 2 on the upper and lower limits of integration for that integration symbol. Now, What we want to do is we want to rewrite the integrand to be as simple as possible, and I think the easiest way to deal with this would be to write it as terms and to go ahead and FOIL. So I'm going to FOIL that, and I get x squared minus 5x plus 4 as a result of that FOILing. Okay, so remember that the first step that I want to do is I want to find the antiderivative. So I can rewrite my integrand there as much however I choose to make it as easy as possible. So now it's going to be easy. We're going to integrate each of these three terms separately. So x squared, we're going to add 1 to the power, divide by the new power. For the second term, we have minus 5 times x, so I'm going to bring down the minus 5. I'm going to add 1 to the exponent, which is going to be x squared, and I'm going to divide by the new exponent. The last term is plus 4. Since it's just a constant, we're just going to multiply by x. Okay, remember the second step is to evaluate at the lower and upper limits of integration. Alright, so I'm just going to write out exactly what I have twice. We're going to replace x with parentheses, and I'm going to do the same thing. I'm going to say minus, and I'm going to put the same thing in the second bracket that I put in the first. Okay, that way I don't accidentally copy part of it, not the whole thing. Those two things should look exactly the same. So the next thing I'm going to do is what number will go in the first parentheses? Well, the upper one, right? So the larger number goes first. Okay, and then the smaller number goes second. Alright, so the nice thing here, my second bracket, 0 cubed is 0, 0 divided by 3 is 0, so this gives me 0. 0 squared is 0 times 5, 0, 0 divided by 2, 0. 4 times 0, 0. So this whole second bracket becomes 0. Really nice. What about the first bracket? So let's work with that. The first bracket, 2 cubed is 8, 8 over 3. 2 squared is 4, 4 times 5 is negative 20 over 2. 4 times 2 is 8. Let's do a little bit of simplifying here. I get 8/3 minus 10 plus 8. I'm not going to worry about the minus 0 because we know that's not going to change anything. Negative 10 plus 8, that's negative 2. Okay, now we're going to combine that with the 8/3. So I need a common denominator. So that's 8/3 minus, let's give this a common denominator of these, so that's minus 6/3. So my final answer here would be 2/3. So this is evaluating that definite integral, which is also the same thing as finding the area between the curve and the x-axis. Alright, so for example 6, we're asked to evaluate the definite integral. Alright, remember definite integral means I have a number at the bottom and the top of that integration symbol. So we don't need to put our plus c's here when we're doing the definite integral. If you weren't sure when to put the c's and when not to put the c's, remember that you could always put the c's and they would end up canceling out. So you can't go wrong with putting the plus c if you accidentally forget. So when in doubt, put the plus c and it'll all take care of itself. So the first thing here is I would like to integrate, right? We want to find the antiderivative. We have x squared minus 1 squared. Well, this sort of looks like something that you would do the u substitution on. However, if you try the u substitution, it turns out that it won't work. So what's something maybe a really easy fix that we could do that we could avoid that u substitution that we love so much? Let's see if we can go a little bit of an easier route. Can't I take that, what's in the parentheses, and just square it? Let's write it out twice. And then we can FOIL that. And if we can get this down to just be some terms, so we don't have to use that u substitution, then this problem would be a lot easier. So let's FOIL. First times the first gives me x to the fourth. Outer times the outer gives me negative x squared. Inner times the inner also gives me negative x squared. And last times the last gives me 1. So if we could write this as terms, then the integration will be simple as using that power rule. We don't have to worry about the use substitution here. This is a really easy fix. Alright, so let's actually then find the antiderivative. Okay, so we're going to do each term separately. So x to the fourth, that's going to be x to the fifth divided by 5. We're going to bring down that constant multiple, negative 2. We're going to add 1 to the exponent, divide by the new exponent. Taking care of that. The last term is just 1. So we know we're going to multiply by the variable that we're using for integration. So that's just going to be x. Okay, so we find the antiderivative. Now, the second step we said was we want to evaluate that antiderivative at the upper and lower limits of integration. Okay, so step 2, I'm going to write down bracket, and I'm going to put down everything except for x. Let's write that 3 a little bit nicer. Oops, I don't need to put that. Okay, so bracket, and then we're going to put minus, and then we're going to put everything that we just wrote again in the brackets. Alright, so which number is going to go into the first bracket? Well, we said the larger number of the two. So I'm going to put 1, 1, and 1. In the second bracket, we're going to put the smaller of the two. So we're going to put minus 1, minus 1, minus 1. Alright, so let's simplify. This should turn out to be pretty nice because of the 1s. 1 to the fifth is just 1. So that's 1 over 5. 1 cubed is just 1, so we get minus 2/3 plus 1 minus. So here we get negative 1 to the fifth power. Well, that's an odd number of negatives, so that turns out to be negative 1/5. Negative 1 to the power of 3, well, that's a negative 1, so it turns out to be a positive 2/3. So negative 1 times negative 2, right there, positive 2 over 3. And then we have minus 1. Okay, before I start giving a common denominator, I'm going to combine some values. So what I'm going to do is I'm going to distribute the negative into the second group, and then we're going to do a lot of combining of the fractions before we start doing anything. So I get minus, well, minus times a minus is a plus, so we get a plus 1/5. And then a minus times a positive 2/3 gives me a negative 2/3. And then a negative times a negative 1 gives me a positive 1. So you might have thought that all of this would cancel out, but actually it does not. Signs change. So let's go ahead and combine things that already have common denominators. So 1/5 plus 1/5 would be 2/5. Negative 2/3 and negative 2/3 gives me negative 4 over 3. Keep the same denominator, add the numerators together. And then the last 1 plus 1, of course, gives us 2. So I just wanted to make that kind of the problem a little bit smaller before I start finding common denominators for everything. So think about this as 2 over 1. The LCD of all of these would be 15. So let's give them all a common denominator of 15. So I get 6 over 15. Multiply top and the bottom here by 5, so I get negative 20 over 15. Multiply top and the bottom here by 15, so I get 30 over 15. So keep the same denominator. Combine all the numerators together. So 6 minus 20, negative 14, plus 30, that gives me a positive 16. Alright, so when we evaluate the definite integral, our final answer would be 16 over 15. And of course, you could also think about this as 1 and 1 over 15. So a mixed number or an improper fraction either way. But this is our final answer for evaluating that definite integral. So evaluating definite integrals, it's exactly the same thing we've been doing. We're going to find an antiderivative first. The last thing we do is just plug in the upper and lower limits of integration, being careful to subtract between the two antiderivatives.